All right, in this explainer, we're going to be taking a look at a really interesting research paper. It's titled Beyond Manual Annotation, a human-AI collaborative framework for medical image segmentation using only better or worse expert feedback. And this work comes from Yizhe Zhang at Nanjing University of Science and Technology.
So here's our plan. First, we'll talk about the big problem, the annotation bottleneck. Then we'll get into the paper's new idea for feedback. After that, we'll break down how their framework actually works, check out the results, and finally, wrap up with some limitations and what could come next.
Okay, let's dive right in. Section 1, the annotation bottleneck. This is really the core challenge that this whole paper is trying to solve.
You know, for deep learning models in medical imaging to work well, they need tons of high-quality, pixel-perfect annotations. But here's the catch. Getting that data is a huge pain. It's incredibly slow, it costs a lot, and it eats up the valuable time of medical experts. This whole manual labeling process is a massive hurdle when we want to actually use these AI tools in the real world, in clinics.
So people have definitely tried to fix this. We've seen things like interactive methods, where experts can just draw scribbles or place points. And more recently, we've got these huge foundation models like SAM, the Segment Anything model. And look, these are great steps forward, but they all share a common problem. They still need an expert to sit there and give very precise manual instructions. It's still a lot of work and mentally taxing for the clinician.
And that's where this paper comes in with a really fresh take. This brings us to their core idea, a new way to think about how humans and AI can work together. The whole approach hinges on this one simple but really powerful question. What if, instead of drawing perfect lines, an expert could just look at 2 attempts from an AI and say, this one is better or this one is worse? Think about it. A clinician can often tell at a glance if a segmentation is an improvement, even if they don't want to spend time fixing every little pixel. It's just a much more natural and less draining way to give feedback.
So what exactly did the researchers bring to the table here? Well, first off, they built a whole framework that learns only from that simple better or worse feedback. That's the core. Second, they created this smart learning-based clicking agent that figures out the best places to click to generate labels. Third, they cleverly used a foundation model to take those few clicks and turn them into a full segmentation. And finally, they proved it works, showing competitive performance on a bunch of public medical datasets.
Okay, so how did they actually build this thing? Let's get into the methodology and the architecture of their collaborative framework.
All right, if you look at the big picture, the whole system is basically a collaborative loop. It starts with the human expert whose only job is to give that simple thumbs up or thumbs down, better or worse. That feedback then trains what they call a clicking agent. This agent's job is to place corrective clicks on the image. Then a foundation model takes those clicks and creates a full segmentation mask, a sort of pseudo-label. And the key is, this is no one-and-done deal. This whole cycle repeats over several rounds, letting the final segmentation model get better and better.
So if we zoom in a little bit, we can see 4 key pieces that make this work. First, they use an adaptable foundation model, Dino V2, which is great for understanding the deep features of the image. Second, there's a label propagation step. This is what turns a few clicks into a complete mask. Third, you've got the star of the show, the clicking agent, which is actually a reinforcement learning agent that learns from the expert's preferences. And fourth, it all happens in a multi-round training process, so the main model gets to learn and improve over time.
Let's talk a bit more about this clicking agent, because it's pretty cool. It's basically framed as a reinforcement learning problem. So the state is what the agent sees, the input image plus whatever the current segmentation mask looks like. The action is simple. It picks a pixel to click. And the reward? Well, that comes straight from the human. It gets a +1 if the human says better and a -1 if they say worse. Over time, the agent uses these rewards to learn a smart strategy for where to place its clicks to get the best results.
Okay, that's the theory. But does it actually work? Let's look at the performance and the results from their experiments.
So here's how they set up their tests. They used 3 different public data sets, one for breast ultrasound, one for skin lesions, and one for polyps. Now, since they didn't have a real expert sitting there for thousands of trials, they simulated one. They created an oracle that used the perfect ground truth answers. This oracle would give a better signal if a click made the segmentation more accurate, specifically if it improved the DICE score, and a worse signal if it didn't. The whole process ran for 5 rounds, with the agent getting to make 5 clicks on each image per round.
And the results? Well, they're pretty clear. This chart shows the DICE score, so higher is better, across the 5 learning rounds. And you can see for all 3 datasets, polyps, skin lesions, and ultrasound, there's a steady climb. This is exactly what you want to see. It shows the framework is learning and getting better with each round of simple, better or worse feedback.
It's not just about the average score getting better, it's also about consistency. This chart gives us a sense of the distribution of scores in the final round for the skin lesion dataset. And what you can see is that the vast majority of the segmentations are landing in the good or excellent range with a score over 0.8. This means the iterative feedback isn't just hitting a few home runs, it's leading to reliably good results across the board.
Numbers are one thing, but let's actually look at some pictures. Here on the breast ultrasound.
And to their credit, the authors are very upfront about a couple of key limitations. First, their simulated expert, the Oracle, is a bit too perfect. It's based purely on the DICE score. A real human expert is going to be more subjective, they'll have biases, and their feedback won't be as clean and consistent. That's a big difference. Second, the algorithm they use for the clicking agent, Reinforce, isn't the most efficient. It can have high variance, meaning it might take a lot of interactions to really learn a good strategy.
But even with those limitations, this is a really promising piece of work. It points towards a future with much more intuitive and scalable ways to create training data. And I think the paper's last sentence really says it all. This kind of approach could potentially shift the human expert's role from a tedious annotator to a high-level critic. And that's a powerful idea, letting the experts guide the AI with simple, high-level feedback instead of getting bogged down in the details.